Hi there and welcome from Ventura, California to today's webinar sponsored by KVH Industries Inside GNSS and Inside Unmanned Systems and hosted by WebAttract. I'm Lori Dearman, Senior Webinar Producer with WebAttract, and I'll be one of your moderators for today's session. And in just a moment, we'll be introducing our panel of thought leaders as today's webinar is about hearing from these leading experts as they discuss the technology roadmap of the photonic integrated chip, a breakthrough in fiber optic gyro design that replaces individual fiber components with an integrated planar optic chip for superior reliability. You'll also have an opportunity to have your questions answered at midpoint and at the end of the presentation during the Ask the Experts panel session with all three of our panelists. Now today we've invited you along with over 260 professionals from 40 countries representing a variety of industries. And over the next 90 minutes, regardless of your industry segment or your location, we are confident you'll find today's webinar of value. Now, before we get started, Richard Fisher, publisher Inside GNSS, Inside Unmanned Systems, would like to take just a moment to welcome you and introduce our sponsor as well as our main moderator for today. So over to you, Richard.
Thanks so much, Lori. On behalf of Inside GNSS, Inside Unmanned Systems, and today's sponsor, KVH Industries, I extend a warm welcome to our audience from around the world for today's webinar. We are delighted you are with us. Now, I'd like to introduce Matt Vargas, Business Development and Sales Manager at KVH Industries, for some opening remarks. Matt.
Good afternoon, Richard. Good afternoon, everybody. First, I'd like to thank and welcome all the participants and panelists on behalf of KVH Industries. We're really glad to have you all here today. KVH is a leading innovator for integrated inertial systems, delivering extremely accurate position and navigation for various tactical platforms, having produced more than 22,000 inertial navigation units for global implementation. KVH Tacnav systems are in use today in a wide variety of applications, ranging from tactical wheeled vehicles, armored and tracked vehicles, and various specialty pointing and stabilization systems. We're continually investing in our product line, which is key in preparing for future market needs and ensuring only the highest level of reliability through extensive testing and qualification. KVH has released our photonic chip-based technology into our Tacnav 3D product line as of Q4 2020. And we'll share a little bit more about the PIC with you today. We hope you find this webinar beneficial to your own developmental efforts, and we thank you again for your participation. Back to you, Richard.
Thank you, Matt. Appreciate that. Now, I'd like to introduce our moderator for today's webinar. It's Alan Cameron, who's the editor-in-chief of Inside GNSS Magazine and the PNT editor for Inside Unmanned Systems. Alan's covered the GNSS, PNT, and autonomous industries as a writer and editor since 2000, focusing on technical issues around continuous, reliable, and assured positioning and navigation. Alan, the floor is yours.
Thank you, Richard, and thank you everyone for attending. Thanks to KVH for sponsoring the webinar. It's going to be a good one. We have some exciting technology to tell you about, our speakers will tell you about, and we'll get to them in just a moment. Matt, whom you've already heard from, Bob Baylog, and Kevin Ricketts. First, let's find out a little bit about our audience. Lori, please.
All right, coming up on your screen is our first poll for today, and we'd like to hear from each of you. What is your biggest concern with GNSS-aided navigation? If you wouldn't mind selecting just one of these options: positional accuracy, spoofing, jamming, or GNSS denied degraded environments. All right, looks like 25% coming in with positional accuracy, 2% spoofing, 11% jamming, and 63% GNSS denied or degraded environments. Any thoughts on these poll responses, Alan?
Quite reasonable, and I would say quite expected, particularly in a military environment, but in almost any environment. First, you want to know whether you have it or not. That would be covered by the GNSS denied or degraded environments. That's your big worry. And spoofing and jamming are also RANs, can largely be subsumed under that main heading as well. A second concern, after you know whether or not you have it, is what kind of accuracy you can obtain from it. Well, good news for 63% of our listeners, well, I'd say for all of our listeners, because we have a solution for GNSS denied and degraded environments coming up. First, we're going to hear from Matt Vargas. You heard a brief word from him before. Matt is Tacnav Business Development and Sales Manager at KVH Industries, where his responsibility is business development, not surprising, within the Inertial Navigation Division. Before joining KVH, he was Vice President of Business Assistance at the Rhode Island Commerce Corporation, and more recently he ran the COVID-19 testing operations for the state of Rhode Island. Thank you, Matt. He has 13 years of experience in small business development, consulting, finance, and military operations. He's worked in challenging domestic and international environments throughout his career, including a deployment in Afghanistan. Matt's a graduate of the United States Military Academy at West Point and has an MBA from the University of Rhode Island. Matt, please take it away.
Thanks so much. I really appreciate the opportunity to present today and talk a little bit about the product history of the Tacnav system. So the history of KVH products is inextricably linked to the evolving nature of navigational challenges on the battlefield. Over time, KVH has provided a breadth of navigation solutions for militaries, foreign and domestic. Love to see the multinational participation today. That gets me fired up, and it's demonstrated by more than 22,000 Tacnav units being fielded in 22 countries and counting. So we're really proud of that impact, and we'll talk a little bit more in detail about those programs today. As a former Army Combat Engineer Officer, I appreciate the intro. I served in a lot of areas that were frequently denied a clear GPS signal. So the idea of joining the KVH team was really a dream come true for me. So over the next few minutes, I'm going to provide a bit of history and context on the evolution of the Tacnav product line. I'm really going to try and emphasize how our products have evolved year over year to meet that market of demand. Apologize in advance if I get a little bit fired up, because of my background. This topic really gets me going if my candor isn't a dead giveaway. So really looking forward to diving in today. So a logical starting point for us military officers is what's our mission? What are the challenges that KVH is working to solve on a continuous basis? So militaries are dependent on GPS and need that position, navigation, and timing alternative structure to be effective in some of these austere environments. The realities of the modern combat environment are such that redundancy and contingency are absolutely mission critical. Warfighters we need backups for our backups, and we have systems galore in vehicles and other tracked assets in those austere environments that need to be able to function in some of the most difficult environments on the globe. So I'm going to talk a little bit about some programs of record where we've worked to solve these problems and provide reliable and seamless alternatives when GPS is not available. So just a little timeline here with some pictures. A logical starting point was one of our first programs in the late 80s. Our initial compass-based systems, it really met the need of the Marine Corps and the Army during that time frame. The next 10 years that followed. And one of the really great manifestations of our product line that I'll talk about on the next slide was the conflict in Iraq and Afghanistan and our compass-based systems on the Humvees for SOCOM, having deployed with special operations. That's being out in some of those areas is super challenging. So being able to provide some positional assurance is a phenomenal feather in our cap historically. And another piece that I'm going to touch on briefly as we go through the presentation is a lot of our legacy compass products are still very effective in modern times because depending on the needs of the vehicle, the type of the system, and the accuracy required, that breadth of need can require a different solution for different vehicle systems for multinational forces. And if budget concerns are in play, we have a breadth of solutions that can answer the mail and be and be incredibly effective. So just moving along, you can see, in the early 2000s, sort of some would describe the peak of the fighting in Iraq and Afghanistan. We had these systems fielded, or compass-based systems fielded, pretty broadly. So I'm going to shift gears just a little bit, but basically, it's in summary, our early integration with AAV7 in the lab in the mid-90s created a solid footing for our products. I mentioned the SOCOM integration as a feather in our cap, and I think it's just really important to emphasize. And I'm going to give you a closer look at one of those. We're not going to delve into the whole array, but it's really kind of unique, especially from my perspective, to look at some of the earlier Tacnav products and how they've evolved into the highly much more technical systems that we have today. And I'm going to spare you some of those details as my brilliant colleagues will go into the engineering detail that I'm sure a lot of you are super excited to get. So this slide dives into sort of a little bit more modern times. So the Tacnav 2 unit was our company's first foray into using a fiber optic gyro-based inertial nav unit. And that set the stage for the development of the Tacnav 3D unit, providing that three-dimensional AP&T. And AP&T, a term for those of you who might not be familiar, assured position, navigation, and timing, sort of the gold standard for our domestic forces in terms of providing positional assurance to our warfighters, but the Tacnav 3D being that premier product to provide that AP&T at a high level when GPS is denied. So one really important takeaway from this slide is our integration with MAPS Gen 1, program of record on our domestic AP&T program. It's a really good example of how we've integrated into the complexities of the DoD AP&T architecture. It's no small feat from an engineering perspective, so we're really happy with that integration, and there's a number of specialty pointing programs that we're working with right now that are a testament to our integration with MAPS Gen 1. So we're really excited about the Tacnav 3D product line and sort of where it's going to take us in terms of rising to meet the needs of the Army, Marine Corps, and other forces as we go here. So by admission, I'm a geography nerd. I actually majored in geography in college, so I'll spare any of the flags quizzing here on this slide, but just another testament to how many countries have fielded our Tacnav products. I know the multinational participation today is really exciting. We love working with militaries, foreign and domestic, to be able to support their vehicle systems to get them where they need to go and provide them with the right product that really meets the intent. But another important note with this multinational sort of breadth of product offering is it demonstrates our integratability. It's a testament to our engineering team that's able to develop and field products in such an array of environments. Really good stuff there. So as promised, I'm going to go into a little bit of detail about some of our compass-based systems. I'm really going to touch on the Tacnav Lite. It kind of gives you a good feel for how the product line has evolved from a physical infrastructure standpoint. So as you can see here, this is the Tacnav Lite with embedded GPS. It's got a physical antenna. The driver control box is something that doesn't exist with the Tacnav 3D. So the structure is going to be materially different, and we'll present the more compact Tacnav 3D box here in a minute, but it's just a good look at the product line and how it's evolved over time. But this product is still heavily used where the quality and the accuracy provided and the price point are really answer the call for a lot of lighter duty military vehicles that have a need for some positional assurance, but maybe it's a large fleet. There's a lot of different vehicles that just need a bit of backup. So this is really a great system, highly fielded, but it will show as well with our moving mat display, we can support the warfighter with automated waypoint configuration. You can actually plug and play different waypoints and navigate in dead reckoning with that product. So really, really some good customized, curated engineering developments that created competitive products that are still highly in demand. Those products also available without GPS embedded, the Tacnav Lite. In the top right corner, you can see our universal multilingual display. Really a great tool. As a former warfighter myself, it really is a sturdy piece of equipment. It can provide steer 2 heading, and it can also provide a solid 10-digit grid in its commander's function to help either the driver or the commander leverage the Tacnav's quality of delivery in a way that's super functional. So we're happy to have those fielded all over the place. They're super sturdy, 4 buttons, really easy to configure and manage. So that brings us to the star of the show today, the Tacnav 3D. Again, I'll give you a little high-level overview, and then my colleagues will dive a bit deeper. So as you can see, the box is very compact, roughly 6 inches by 8 inches for reference. I know it's tough to tell in the specific photos, but it packs a punch in that small footprint. So included in that box are all the elements required to provide positional accuracy with GNSS, 2 to 3 meters RMS, and then DR accuracy within 0.2% of distance traveled. And we've demonstrated that in a number of austere environments, critical training nodes, multinational training exercises where we've proven that. The team's going to show you some pretty cool videos of the Tacnav 3D in action in the field, really to give you a flavor for what it can do in some tough environments. Heading accuracy within 0.05 degrees root mean square with GNSS, also achievable with the unit, and then pitch roll accuracy to 0.05 degrees as well. So really a quality of delivery in a small footprint. The system's easily integratable with external GPS, although it has GPS in it. Several different battle management systems commonly used today. Dagger Plugger, Micro Dagger V, Blue Force Tracker, stuff that those of us in the service have seen. And I'm dating myself a little bit maybe with the plugger, but we have a really good integratable platform with a lot of external GPS mechanisms that can feed into the Tacnav. So folks, I'm going to spare you any more technical detail as my colleagues are going to steal the show here in a moment. But to summarize, we have a wide range of systems that are available to meet the needs of the fighting forces out in the field. I'm really proud to have delivered this information today. Really proud to keep working to meet the needs of armed forces, foreign and domestic. Happy now to hand it back over to Alan, and really wanted to thank everyone for coming today.
Thanks, Matt. And now to take that deeper dive into the technical innards of Tacnav 3D, as Matt has promised, we're going to hear from Robert Baylog. Bob is the Chief Technology Officer at KVH Industries. He served in that capacity for 11 years. Prior to that, he was Vice President of Engineering Satellite Products for the company. Before that, he headed his own engineering contract services company, Automation Services, specializing in a wide range of automation solutions. He was also Vice President of Engineering at ADE Corporation and held several positions at Speedline Technologies, a supplier of capital equipment to the electronics assembly industry. Mr. Baylog has served on the board of directors of the Surface Mount Equipment Manufacturers Association. He holds 14 U.S. patents and a Bachelor's of Science degree in computer science from Purdue University. Bob, let's go deep.
Excellent. Thank you very much, Alan. Well, hopefully Matt's given a really good product overview, and my intention is to go a little bit deeper and talk to you about KVH's Tacnav product line, and more specifically how our photonics integrated chip technology is really help make that an even better product. As you already know, position, navigation, timing are vital to mission capability. Tacnav is an inertial sensor-based solution, which gives you the ability to function in GPS-denied or degraded environments. This is extremely important as GNSS signals can be blocked by buildings, tunnels, cargo trucks, intentionally jammed or spoofed, and the fog-based inertial sensors will deliver a situational awareness when other sensors are degraded, unavailable, or jammed. The sensor technology embedded within the Tacnav product, to go one level deeper, is the KVH fiber optic gyro-based P1775 Imu. The high accuracy and stability of the fog-based Imu provide the necessary precision to function in a GNSS denied environment for extended periods of time. More specifically, we're able to maintain a 0.2% of the distance traveled while dead reckoning. And I know that's something Matt mentioned earlier, and Kevin's going to follow up with the next presentation and actually show you some of the details and some of the test runs of that performance. So integrating this P1775, we're delivering more reliability. We're helping maintain and improve the accuracy and performance of the product. And we're giving you 100% situational awareness with or without GNSS. So as I keep peeling back this onion and we go a little bit deeper, we're going to talk about the P1775 Imu. The new P1775 Imu is based, again, on that PIC technology, the photonics integrated chip. This product, this IMU, is offered with 30G, 16G, and 10G accelerometers, which are giving us more dynamic and accurate sensor performance, improving our navigational capabilities. This product provides more environmental robustness in vibration and in shock, improved reliability and repeatability. We're achieving an order of magnitude better drift or bias instability and velocity random walk than in prior inertial products. We're also seeing more than 10 times higher accuracy than a MEMS-based inertial measurement unit. So this really is the heart of the Tacnav 3D. So just to talk quickly before I go the next level deeper on the IMU, I also did want to mention that KVH's entire product line of fiber optic gyros, IMUs, and individual sensors are all now photonic based products. And of course, this is giving us compact, rugged, solid state, ultra high bandwidth performance out of the entire product line. The photonics fog, is the building block of this entire product line. So with that, I will pass it back to you, Alan, before I jump into the guts of the photonics integrated chip.
Terrific, Bob. We'll pause now and field a few questions. First of all, Bob, you've moved the company, or the company has moved pretty wholeheartedly into PIC technology. Are there specific autonomous applications for which photonics-based products are particularly well suited?
Well, the photonics-based products are really well suited for almost any application for our fog products, because really it's just building on the performance of those sensors. We currently operate, our customers operate those fog sensors within autonomous vehicles, cars, aircraft, land, sea, air, you name it. So it's not just the topic we're on today, which is, of course, military Tacnav, which is extremely well suited for. The PIC enhances the product's performance and reliability really across our entire customer base. So it's been a really, really fantastic development.
Well, our readers at Inside Unmanned Systems will be really interested to hear about that. Matt, referring back to your presentation, you talked about the complex DoD PNT environment. Given the more open architecture in DoD vehicle systems procurement, how does that affect the your product line, positively or negatively?
No, I think it's a positive impact overall. As I mentioned, our product is highly integratable via a number of mediums, so any of that latitude just gives us a greater chance of being competitive, because we know we can rise to meet, you know, whatever integration need there may be for that platform. So we welcome a more open architecture. I think sometimes, you know, in the bid process it can be a bit more closed off, and then that, you know, really makes it difficult if you're not sort of baked into the spec. So anything that's more open just gives our engineering team a chance to shine. So we're bullish about it.
I'll bet. Coming from the inside GNSS side of my job description, here's the question I always want to know of anybody. What type of GNSS receivers are used in the KVH solutions? Defense, commercial, etc.?
From an external GPS standpoint, I mentioned a few. Like I said, I'm dating myself with the plugger, but plugger Dagger, micro Dagger V, Blue Force Tracker. You know, we've got configurations that are feeding that data into our system. So we have the internal capability, but, you know, generally for our domestic use, there's an external GPS and one of those flavors to feed into the Tacnav.
All right, and turning back to you, Bob, what's the biggest advantage of photonic-based fogs over traditional fogs? If you could single out one.
Oh, the biggest advantage, I'm going to say, is just stability of the product and improved performance. And I guess say performance and reliability. It's hard to say just one because it is such a fantastic enabling technology.
All right, well, we've quizzed the experts a bit. Let's quiz the audience a bit more. Lori, what's our next poll question?
Absolutely. Coming up on the screen is that second poll question. I'd like to hear from each of you. On which type of applications are you currently working? Land, aerial, marine, or subsea? And it looks like we're coming in with 73% land, 50% aerial, 23% marine, and 13% subsea. Alan?
Well, since those add up to a pretty big number, I'd say that a lot of our audience is working on more than one application. That's my first guess. There are no wrong answers to this question, of course, because photonic integrated chip technology works well in all of these environments. But as Matt has pointed out, we're focusing at the moment, at least, primarily on land applications and on light military vehicles. If you want to pick out one specialty within that area, of course, all military ground vehicles have had a great deal of success with KVH products. Bob, let's return to your presentation, and I encourage you to go as deep as you possibly can because we have a very technically oriented audience. Take it away.
Fantastic. Thank you very much, Alan. So the question is, what makes the P1775 different? You know, to get deep into it, the difference is the heart of that fiber optic gyro implementation, and that's our photonic integrated chip, or PIC as we've been calling it for short. In the PIC, all of our discrete optical components that make up the rotational sensing circuit have been integrated into a single chip. The couplers, the polarizer, that were all previously fabricated individually with a high-touch labor content are now produced at a wafer scale utilizing a semiconductor fabrication process. So I draw your attention to the diagram on my slide here. In the upper right-hand corner, what you'll see is the sensing, the optical circuit of a fiber optic gyro. You'll see that there's an SLD, which is our light source, in the upper left corner of that diagram. There's a detector for the returning light just below it. The SLD passes through coupler number 1, through a linear polarizer, through a second coupler, into the sensing coil, and then traverses around a PZT modulator. And then as the light retraces its path back through the circuit, it ends up at the detector. So this piece of optics is able to very, very accurately sense motion and rotation of that coil. So what we've done with the PIC technology is we've actually taken the couplers, the polarizers, or the couplers and polarizer, and moved them into a chip solution. So really what we're doing now is attaching the SLD and the detector to that chip, and then the coil and modulator make the other end of the connection. So what we've done is we've eliminated a number of optical splices. We've eliminated, as I mentioned, the discrete polarizer, the discrete couplers, and we've eliminated an awful lot of manual labor that's involved in creating those high precision optical components. So the net result is reduced optical loss. The reduced optical loss has a couple real-world impacts. It removes the loss of power. So as we're using the SLD, we've got increased lifetime. We're not required to run the SLD as hot as we normally would, so we're able to reduce that power. It gives us a longer lifetime out of the SLD. We've removed all of the chances for potential failures and things like that in the optical system. So it really is a fantastic consolidation of a bunch of discrete components. So on to the rest of the process. The PIC technology really pushed us forward into a new level of performance by all the different methods I've mentioned so far. We have to support that with a full suite of new test and characterization processes to ensure that we've got consistency. So in this slide, we're showing you a picture on the left-hand side of one of the engineering clean room laboratories, where we'll do a bunch of different measurements and characterizations of things like power, mode fields, spectral densities, alignment sensitivities, polarization analysis. The picture in the upper right-hand side of the slide is a picture of some of that test equipment in action during some of the characterization. The next slide here is a glimpse into some of the actual analysis tools that are used during the development of the PIC. We're showing a few examples of measuring spectral density, mode field, and in the case of the graph on the right-hand side, what we're actually doing is an alignment tolerance analysis. As we bond the fiber to the chip, or as we bond light sources to the chip, it's important for us that we maintain the certain power levels and we maintain all of the other optical characteristics that are important to the performance of the gyro. So we're able to characterize that, design the mode field so that we've got tolerance to physical misalignment, and make sure that the system maintains performance all throughout the manufacturing process. So what else does the optical chip provide for us? The optical chip provides increased repeatability when compared to fiber-based components. We're more environmentally insensitive when compared to fiber components that are hand manufactured. We've got reduced bend loss, better split ratios on those couplers, less wavelength dependent loss in the optical circuit. The monolithic integration creates a virtually spliceless gyro, eliminating those potential failure modes and reducing assembly labor in the process. And more importantly, this is a scalable design via a wafer fabrication process. So we're utilizing wafer scale fabrication that allows for order of magnitude increases in production runs. So we're moving these sensors to a mass production, low cost, high volume method of fabrication. Some of the things that come along with that, the semiconductor-based quality structure, which provides us lot, wafer, and pick level verification. We've got test structures on those wafers. We can validate, sample, and make sure that our process stays in control, and we can validate with those control structures. And we're able to utilize mature integration and packaging methods, enabling high repeatability in the manufacturing process. So in conclusion, you take all of those steps, you take all the information on the PIC, the P1775, you roll it all up, and you can see how this new KVH patented technology helps us deliver new state-of-the-art products with better performance and reliability than has ever been available before. We're very excited where this technology is going, and we're very much looking forward to a long line of products based on the PIC technology in the years to come. And I hope that provided some important information for everybody. Alan, back to you.
Thanks, Bob. Really, this photonic integrated chip technology is amazing. I would like to spend more time on it, but we're going to keep moving. We're going to hear next from Kevin Ricketts, the Director of Tacnav Product Development at KVH Industries. Prior to joining KVH, Kevin was Director of Engineering at Comprehensive Power, a dynamic energy solutions provider for military, marine, renewable energy, and the oil and gas industries. He has extensive experience in program and product management. He was also with North Star Marine Electronics, where he held numerous positions, including Director of Engineering. And among other duties, he was responsible for research and development. He's a graduate of Northeastern University and Wentworth Institute of Technology, and he's also a licensed U.S. Coast Guard captain. Kevin, it's yours.
Thank you for the introduction, Alan. I'll be covering what makes up the Tacnav 3D system internally as well as externally. Its connectivity in a typical military ground vehicle, and then we'll review some of the real-life performance testing examples. The Tacnav 3D is purpose-built for Army ground vehicles. At the heart of its architecture is the sensor nav fusion engine. The sensor nav fusion engine combines sensory data that helps reduce uncertainty in position and attitude determination. It takes on the task of combining the data from multiple sensors to determine the most accurate nav and attitude solution. Within the KVH P1775 flagship Imu, we have 9 degrees of freedom, and that is 3-axis PIC fiber optic gyros, 3-axis MEMS accelerometer, and a 3-axis MEMS magnetometer. We also have an internal altimeter, which is a pressure sensor that provides a 10th degree of freedom in our system. Our internal GNSS is a 336 channel quad constellation capable module, which allows us to offer GPS, Galileo, GLONASS, and Beidou, any combination of those systems. So it's available as a quad constellation unit, tri-constellation, dual constellation, or single constellation, meaning GPS only. And that depends on customer preference. In terms of external interfaces that are required for precise navigation, the Tacnav 3D accepts speed sensor inputs in the form of J1939 CAN bus speed and gear, wheel tick odometer sensors, ABS sensors, or OBD2. These are all the current sensor inputs that we currently support. Additionally, we support what is normally a customer furnished piece of equipment, an optional dagger or plugger, as Matt had mentioned earlier, or a micro dagger. Depending on the customer's preference, this gives you a path to SASM or ENCODE external GPS. The Tacnav 3D is also designed, its internal electronics and packaging are militarized and ruggedized to meet MIL standard 810G environmental, 461F EMC, and 1275E characteristics of DC electric systems. In terms of the Tacnav 3D's extensive connectivity, we support a wealth of connectivity options, actually. Matt talked a little bit about our display products, the UMD and the MMD. Here are a few common system configuration options highlighting our display offerings. On the top right of the slide, you'll see an MMD and a UMD in this configuration. And in the bottom pictorial, you'll see two UMDs, depending on customer preference again. It's important that we note here that the Tacnav 3D can operate as a standalone system. So in other words, you attach a KVH display or two to the system, and it operates standalone. Additionally, we can connect to the customer BMS, which we call the battle management system. The battle management systems interfacing that you'll typically come across in military ground vehicles are RS-422, J1939 CAN bus, or Ethernet. We support all of these interfaces currently. In the terms of J1939, some customers have expressed interest in separating navigation and targeting into one CAN bus from the vehicle and drivetrain centric data running on the other CAN bus. Other customers have expressed interest in redundancy where they put everything on each CAN bus. For turreted vehicles, we support a turret angle encoder interface as well as laser rangefinder. When you know your turret angle and your range to target via those interfaces, and you know your own vehicle position and attitude, we can return target position info to the commander. We support a number of communications LRF manufacturer protocols, by the way. In the case where an external GPS is required, usually in the form of a dagger, we provide the connection and inclusion to our Fusion nav engine. For precise timing apps, in the absence of GPS, our CSAC device provides a spec of 1 microsecond drift after 5 hours. Moving on to real-life performance testing. To complement our extensive laboratory simulation, which include sensor modeling and analysis, we perform extensive real-life testing scenarios. During these varied test runs, we measure performance and we record all sensor data for later playback simulation. All sensor inputs are recorded, including the raw data from the GNSS. This allows us to create a library of these test cases, which is key to high quality system software regression testing. In this first example, this is one of a very long open loop test case. We start the run at the KVH factory in Middletown, and we end at the base of Mount Washington, New Hampshire, which is the tallest mountain in the Northeast U.S. The DR performance here is better than specified performance based on ideal conditions. So this run was approximately 360 kilometers, and the final position error ended up being 64 meters, which is 0.02%, which far exceeds our 0.2% of distance traveled specification. Once we get to the bottom of Mount Washington, it offers a drastic elevation change and an opportunity to test our 3D performance without GNSS. Let's roll the video. So here at the beginning of the run, GNSS is enabled. We're using our GeoFog Manager tool, and notice that we can monitor the GNSS fixed, the number of satellites tracked, constellations used, and so on and so forth. Here, we disconnect GNSS for the rest of the run up the mountain, and we'll track this all the way to the top. If we look deeper into the sub-menus, we can find all the raw sensor data in real time, including satellites, accelerometers, gyros, magnetometers, pressure sensor, and temp data. In the absence of time, we won't dive into all that now, but that is available as raw data. You can see that once we entered, once we exited GNSS mode, that the SACS tracked indicator goes to 0, and we continue in DR mode. The GeoFog Manager is a very powerful tool that can be used for real-time monitoring and data logging. It allows us to display live data on maps and has extensive logging capability, including all raw sensor data for post-processing. The program can convert the log data to either KML or GPX map files. Here we're using a Bing map. This tool is commonly used by both customers and KVH personnel for vehicle integration and system troubleshooting. Looking at the test results here, the bottom elevation of this test run was 450 meters, and the elevation at the top of the mountain was 1,868 meters with an average gradient of 11.6%. The total distance traveled was 24.25 kilometers, and the final error at the top of the mountain was 36.4 meters, yielding a total distance traveled error of 0.15%. Here we have another example of a different type of testing. Here we, when our CTO says he'd like us to record some off-road testing and offers his own personal Jeep as a test vehicle, we really got to have some fun. This is just an excerpt of a 14-kilometer off-road test run. It included many obstacles, deep mud, water holes, and rocky patches. We'll start the video now. Position accuracy while navigating off-road without GPS can suffer dramatically from wheel slip and grabbing. Here we force these conditions and we recorded the results.
Yeah, but you didn't say anything about deep mud when you took my
Deep
truck.
mud. It was deep water and deep mud. And we forgot to wash Bob's vehicle when we were done. So the total distance traveled here was approximately 14 kilometers. The error, 24 meters, which yields about 0.17% of distance traveled. We purposely introduced significant wheel slip and crabbing, and the post-processing indicated this. When we look at the odometer, it indicated significantly longer than actual distance traveled. The Nav Fusion engine is able to overcome that using the other associated sensors. In particular, accelerometers, they sense the force and they know that the odometer couldn't possibly be traveling the distance that that it was telling the system that it was. We have one more test case example here. This was observed in the downtown Providence, Rhode Island, urban canyon. It's a particularly compelling test case to show off our Tacnav system performance while integrated with external GPS. So here, this is with GPS, and you'll notice that the red plot is the GPS position output, where the Tacnav position output is in blue. GPS is known to suffer from blockages due to nearby buildings, tree cover, passing trucks, etc. So this is a pretty extreme example of an urban canyon. In this example, position errors are noticed due to blockages and multipath, otherwise known as reflections. It's important to note here that the GPS figure of merit during this time indicated that the system was good. The GPS was telling us that your position is good, yet these wild excursions are taking place. And I'll also note that this is not just one GPS that acts this way, but we've tested many of the commonly externally connected GPS systems that the military uses currently, and we see similar results for multiple product variants. The Tacnav 3D engine is always calculating and outputting its own position even when GPS is available. In conclusion, as we find new opportunities to improve our system performance, extensive sensor modeling and simulation accented with real-life test data provides us with very high-quality regression testing capability. And I'll turn this over to you, Alan.
All right, thanks very much. That last slide was really interesting, showing how going around sort of the outside, the perimeter of the urban environment, everything seems fine, but as soon as you dive right into it, whoa, GPS jumps right off the street, and the Tacnav kept you where you wanted to be. We have a slide of resources for you here. A number of things to follow up with more in depth, or to have to print out and review with your colleagues. Advantages of photonic chip technology, accurate heading for autonomous navigation, and lightening the war fighter's burden with trusted navigation to the new Titan. Let's have one final poll for the audience. Please, Lori.
All right, let's do it. Coming up on your screen is that third and final poll. The applications with which you work, primarily autonomous or manned. Let's go ahead and select one of those two options. Looks like we have 45% coming in with autonomous and 55% manned. Alan, any thoughts here?
Well, just that it's pretty interesting. That's a fairly even split. Of course, the manned applications are sort of top of mind, but the autonomous applications are gaining ground furiously, one might say. There are just so many applications, markets and so forth that autonomy can be, that autonomy can address, that as readers of Inside Unmanned Systems know, it's just explosive. Well, we're going to turn now to audience questions. I'm going to start with a question for Bob. What are KVH's future plans for PIC technology integration into its products?
Well, as you've seen so far, we've integrated the basic coupler polarizer, coupler loop into the existing sensor products. Right now, there's an extensive amount of R&D that's going into how much further we can take this. We've had some fantastic progress with additional integrations into that photonics chip. And at some point in the future, we hope to have even more components that go into that optical circuit, the optical loop of the fog, integrated into that, giving us an even more monolithic design. At some point, ideally, we'd love to get this down to an optics chip, an electronics chip. That may be a little bit off, but we're charging down that road, and we've got some fantastic scientists hard at work up in the lab right now.
Question for Kevin. Will the PIC make KVH's products more competitive in swap C?
Yes, so PIC manufacturing reduces size, number of components, and labor content. It also increases manufacturing yield and throughput. So yes, it will be more competitive in swap C overall.
And going back to Bob, how does PIC technology help fogs compete against MEMS gyro products? We hear a lot about MEMS technology.
Yeah, well, I think it probably goes back a little bit to the question you just asked Kevin. As you would imagine, going from a individual discrete component fabricated optics loop on the product into a semiconductor, batch built wafer-based manufacturing process, it's giving us the ability and volume to really work on manufacturing costs. Right, so it has the side effect of making a more reproducible product, but it also drives out those production costs. So a lot of the other future R&D things I spoke about would also help drive toward that lower cost. Now, if you're talking about MEMS, really what everyone with MEMS is trying to do is go up the food chain, so to speak, to higher performance. And what we're actually doing is we're taking our sensor products to an even higher level performance, and we're driving the cost down the ladder to be even more competitive into markets where MEMS sensors play. So in the future, I wouldn't be surprised to see a lot more direct competition between precision fogs and in some of the higher end MEMS products. So it's pretty exciting for us.
And another one for Kevin. Are KVH's Tacnav systems for military use only, or can anyone buy them?
So the Tacnav 3D is ITAR controlled under the U.S. munitions list. All Tacnav products are currently ITAR controlled. KVH does have a line of INS products that Matt could tell us about that are rated commercial off the shelf.
Okay, Bob. Question about stationary or low rotation rates. How well does how does your fog sensor handle those, stationary or low rotation rates?
Yeah, the fog really, the actual sensor, the interferometry doesn't really care whether it's stationary or it's a low rotation rate. It's an extremely stable product. It's extremely precise. In fact, even when you're stationary, you're likely picking up rotation of the planet sensing as well. So, as you would design it into your application, as we've done in things like Tacnav 3D, you need to take things like that into account. And of course, the product's fully calibrated and calibrated over temperatures and temperature rate of changes. It's designed to handle that sort of thing. So there's no particular concern at stationary or low rotation rates. Again, of course, there's a lot of work that can be done at the application level to further enhance that sort of thing. If you take a product like Tacnav 3D, we've gone to great lengths to ensure that we're monitoring gyro bias, we're monitoring any sort of drift in the sensing rates in the product. And that's really what helps us achieve that extraordinary 0.2% over distance traveled. So yeah, it's particularly well suited for that sort of thing.
And Bob, since we got you, one more question. Actually, I think most of these questions coming up are may be for you. Inside Tacnav 3D, there are 3 standalone fogs, one for each axis, each one with its own pick. Is that correct?
That is absolutely correct. Within a Tacnav 3D, there's a P1775, which is comprised of 3 individual sensing coils. We lovingly refer to them as the pucks. So those individual pucks have their own optical circuits, which each contain a pick.
And is the pick less sensitive to changes in ambient temperature or the rate of change of temperature than traditional designs?
It's actually a very good question. Just by the nature of the pick's design or its implementation really being contained within that single chip, it's a little bit easier for us to mount it within the coil in an area where we can better maintain thermal gradients, thermal stability of that optical circuit as the product encounters temperature changes. The discrete components are typically built and then routed within the coil area. And they typically tend to be a little more spread out and probably not as consistently positioned in exactly the same locations within the mechanism. And again, we're talking about a sensor that's so extremely accurate that even the most minute things like temperature gradients have to all be accounted for in the design. So the answer is yes, it does actually help us maintain that temperature stability and that thermal gradient, or minimize any thermal gradient in the product. I can't really throw any numbers at it yet, but as we get a little bit more data down the road, we'll be able to publish some of that. But excellent question.
And Bob, another one from the same listener. What's the role of the magnetometer in calculating the position and attitude of the vehicle?
So I'm going to take it that these questions are that I didn't cover enough information, or maybe I covered too much information. The magnetometers within the Tacnav 3D serve a couple different roles. They're used, of course, for background sensor fusion within the Kalman filtering. So the magnetometers are involved. There's a 3-axis magnetometer in there that's measuring position of the actual unit. There are actual magnetometers involved in the sensing as well within the IMU, and some of that's used for internal calibration of the fiber optic coils and things like that. So there's a multitude of uses for magnetometers that are in there, but general to say it's all fused in through our solution.
And for any of you gentlemen at KVH, someone wants to know about, of course, the big question, or a big question with GNSS is how well they work indoors. What about your products? Have you tested them in indoor environments?
If we're talking about Tacnav 3D, they get tested indoors routinely as military vehicles are put away. You know, at the end of the day, they go into a garage or actually the manufacturer's facility. So they'll be, you know, the INS kicks in indoors, the vehicle gets turned around and comes back out. It takes a while for GPS to reacquire. So in that respect, Tacnav 3D gets tested indoors. And there's also some pretty extensive tunnel testing that's been done as well, you know, where obviously you'll lose your GNSS convergence and, you know, traversing in and out of tunnels. But I'm not sure if the question was related to or specific to Tacnav 3D or not.
Yeah, I think it was, and you've raised an interesting point, Matt. This comes up a lot in consumer navigation, consumer vehicle navigation, particularly as they try to develop autonomy, and also in navigation mapping. tunnels. What the challenges posed by tunnels? If you park a vehicle in a garage, you do have a little bit of supplementary information as to where it is, although you still want to know. But if you're entering one end of a tunnel and coming out the other end, you really need to know quite quickly, as soon as you're out the other end, where you are, and obviously GNSS can take some time to reacquire. Can any of you gentlemen provide any more specifics about tunnel testing or tunnel performance of
I could probably shed a little bit of light on that for you. So if you're driving along and let's just say you're in your car and you've got your GPS and you drive into a tunnel, right? You drive into a tunnel, you lose your GPS signal. Your car is going to assume that you're staying in the tunnel because it's going to operate on a road-locked system. It's going to assume you didn't drive off the road. And it's, in some cases, going to use information wheel speed sensor from the vehicle, right? The integrated GPSs will do that. So it'll actually be able to maintain your position within the tunnel, but purely based on your distance traveled and your speed. So if we talk about a Tacnav product where we're not talking about road-locked navigation, if you drive into a tunnel, that wheel speed sensor is extremely important, right? Because now we're able to go ahead and calculate distance traveled. If you were to drive in an unmapped or unroad-locked situation without wheel speed sensors, now you've got the challenge of being able to measure acceleration of the vehicle, which of course you'd have to back calculate your distance and your speeds, which inherently starts introducing errors into the equation. So all of our Tacnav systems are designed to operate with those wheel speed sensors to give you that additional performance. So I hope that answers the question.
Yeah, I think it does. Good answer. We've run through our material, and I'm going to wind up the webinar now. Thanks to everyone in our audience for attending, and we'll just go around the panel and ask for concluding comments from any of you gentlemen, starting with you, Matt.
No, I just wanted to thank everyone. I mean, really phenomenal content today. Thanks for the opportunity. Obviously, pretty passionate about this product line and getting it out there. So feel free to follow up if any folks have interest. Thanks again.
And Bob?
I'd like to thank everybody for giving me the opportunity to explain some of the cool technology that we're working on. I hope everybody learned something. I look forward to future presentations as we continue to develop new products and exciting things over here at KVH. And I look forward to Alan spreading the questions around to the rest of my team next time.
Well, we'll try to do that.
No, that was a good time. I enjoyed it. Thank you.
Okay. And last comment from you, Kevin.
Thank you all for attending. It was a pleasure to describe the inner workings of our product and its performance under varied test conditions. Please feel free to contact KVH with any further questions you might have. We love to develop products that delight our customers. And again, thank you all for attending.
All right, well, that does it for today's webinar. You can also look to the future issue of Inside Unmanned Systems for a webinar recap. We'll briefly cover the highlights of the webinar, and that will help spread the word further, and you can share this information with your colleagues and any other interested parties. Well, this is Alan Cameron from Inside GNSS and Inside Unmanned Systems. I'd like to thank KVH once again for both sponsoring and presenting the content of this webinar. The uses of inertial navigation are increasing and widening, and the advances that have been made in the technology are truly staggering. And PIC is just the latest and one of the most exciting. We're glad you could join us for this look at photonic integrated chip technology. And once again, thank you for attending. Lori?
All right. Thank you, Alan. And Most importantly, again, thank you for joining us. This is Lori Dearman saying, hope we see you on the next one. Bye for now.